So we have spent the last, feels like forever, on derivations. Today is the last day of hardcore derivation. All right. By the end of today, we should have in hand the famous Navier Stokes equations and the also less famous but less interesting Euler Equations. Okay. We're going to get these. It's relatively few steps from where we left off last time to where we're going to end up today. The idea is we're going to take our momentum equation we ended up with last time. Okay, it was general equations of motion, and we're going to plug in a couple of substitutions based on things we've already learned to come up with these two different sets of equations. So, kind of a quick recap. Let me bounce back to the slide we had here. So, right, last time we said the momentum equation, right, is essentially F equals ma for a little tiny particle of fluid. Those F terms, right, the forces are surface forces. Those come from the stresses on a fluid particle, namely normal stresses and shearing stresses. Okay. Additionally, there are body forces due to things like gravity, magnetism, centripetal acceleration. In this case, we're only worrying about gravity. And then if you sum those forces up, you should get to mass times acceleration. So surface forces, right, we wrote out using first order Taylor series expansion. We said that the force on a little tiny cube of fluid with size or with side lengths of delta x, delta y, delta z can be written like this. The body force, right, is just rho times the volume times gravity, so mg. And then summing those together, we should get rho times the volume, so the mass times the acceleration in x, y, z. These last terms here, remember we said the acceleration of a particle can be written as the material derivative, capital d u dt, dv dt, dz, or dw dt. And then because we know the definition of the material derivative, we can write those out using that. Then the next step was, say we've got these pesky delta x, delta y, delta z's in every single term. Okay, that represents the tiny volume. So if we cancel all of those out, we end up with the equations of motion with body force plus surface force per unit volume, because we canceled out that little unit volume, is equal to density times the acceleration. All right. So our task today, okay, is to figure out how we can make these usable. Why aren't they usable as is? Well, if we went through the process of counting up how many unknowns we've got here, we'd see we've got 12 unknown quantities, only 3 equations to tackle them. Right? That's not an amenable situation. We can't deal with that. Right? Mathematically, it's an ill-posed problem. There's no way we can uniquely solve for velocities, pressures, stresses, given only these 3 equations. So we have a couple of simplifications that we can make in one case, and we have a model of Newtonian flow in the next case. So the first simplification that we're gonna plug in here is assume inviscid flow. Okay. So let me go ahead, right? Simplification. All right. So inviscid flow, right, means the viscosity is assumed to be 0 or negligible. And if there's no viscosity, there's going to be no shear stress, right? You can't have any friction if the fluid's frictional coefficient goes to 0. And so with that, we can cancel out all of these shear stress terms. Likewise, the normal stresses are left here, the sigma xx, sigma yy, sigma zz. We're going to say that sigma xx, sigma yy, sigma zz are both all are all equal and equal to negative pressure. All right, we talked a little bit about this last time, being that pressure is positive if, like, a positive pressure tends to cause compression. And the way that we drew these sigma xx, sigma yi, sigma zz was positive if they were pulling outward on a fluid particle. So we need a negative sign just to rectify those two, the differences in signs. And so with that, right, if we just cancel this out and plug in a negative p everywhere that we have one of these normal stresses, then we end up with, oops. I'm supposed to have gotten rid of, let me go ahead and just write it down. We end up with, if tau ij is equal to 0 for I not equal to j, okay, so shear stresses disappear. We get the Euler Equations of motion. Okay, so these are important equations to have written down, and the way we write them is rho gx minus dp dx is equal to rho du dt plus u d dx plus v d dy plus w d dz u u u. You'll learn quickly that probably the worst part about this chapter is how long it takes to write out the equations. So we're going to take a few minutes here. Rho gy minus p dy to rho v dt plus v dy plus e, sorry, that's ddx v y plus w d dz v v v and rho g z z rho okay. So we've clearly got, right, the x direction here, the y direction, and the z direction. And instead, you've got body force per unit volume, surface force per unit volume, and since we don't have shear stress, the only surface forces come from pressures. And then we have density times the acceleration. Okay. So we can also write this more compactly. Okay, we can boil all of this down into a much more, much friendlier expression. We say rho g minus grad p is equal to rho dv dt. Okay, so this, right, vector expression expands into this whole mess right here because it contains three components, and we've repacked that material derivative back into the ddt term. And so this is it. This is Euler Equations. There's not a whole lot more to say about them, except that they are valid for inviscid fluids, okay, where the only surface forces present are pressures. So no shear stresses. I don't, again, since I wasn't here giving the lecture on the hydrostatics, okay, and the fluid statics, I'm not sure whether this point was really made. But one of the things I like to point out early in chapter 2, right, when you're deriving the hydrostatic equilibrium equation, is that we wrote that as, right, for fluid statics, rho g, sorry, that needs to be a vector. Gravitational acceleration is a vector. Rho g minus grad p was equal to 0. Okay, this is what the book derives, doing essentially F equals ma in an unmoving fluid. And, right, for statics, and as you say, A equals 0. So this is exactly equivalent to the difference between normal statics and dynamics that you've covered before. Sum of the forces equals 0 versus sum of the forces equals MA. Okay? For fluid statics, 0. Now we're talking about there being accelerations. Okay. So Euler's equations of motion, we've gotten rid of all the shear stresses, right? Of which there are 1, 2, 3, 4, 5, 6, right? So we have eliminated 6 of the unknowns by saying that they're 0. That still leaves 6 of our original 12. Okay, so we've got 6 unknowns and still only 3 equations to handle them. So this is still an extremely complex set of equations. Even though we've simplified them a lot and they describe a much simpler fluid, we've still got coupled nonlinear differential equations for which there's no universal solution. However, we'll see in a second that these are still a lot easier to handle, or these are still, elimination of those terms makes these much friendlier than the full-blown Navier-Stokes equations. So that begs the question, when would we want to use the Euler equations? When do these actually kick in, right? All fluids are viscous. This idea of an inviscid fluid is it's fictional, right? When is this is the equation we would, or this is the question we would ask ourselves, and the answer is surprisingly often, right? When we said we're going to assume that the fluid is inviscid, what that did for us is allow us to eliminate the shear stresses from the equations. The other way you can end up with a flow that has no shear stresses is if there's no velocity gradients. Okay, there are no shear stresses present in a uniform flow because the velocity is constant throughout, so there's no friction between fluid particles. So the question is when velocity gradients go towards 0, which happens surprisingly often. So I've got here a little illustration of cases where we can go ahead and use these sorts of assumptions of an inviscid fluid. So, for example, if we were to look at this, flow around a streamlined, well, I guess a semi-streamlined body here. This might be like one of the newer designs of bridge pilings that are designed for some streamlining. Upstream of this thing, okay, if we assume we have a current flowing in, there's no velocity gradients present there. And because of that, there are no shear stresses. It's not until you hit the body and you end up with the no-slip condition, right, where the fluid sticks to the body and it has to go from that constant velocity out here to the 0 in the body, you end up with this thin little region where you have velocity gradients, and it's only in that thin region and downstream of that region, okay, that you have to worry about the shear stresses. So this enables us to, for example, take a realistic problem and split it into 2 components. You'd say this relatively small region of space near a solid object or near a no-slip boundary, that's the only place we need to worry about viscosity and the shear stresses that it creates. And throughout the rest of the fluid, because the flow doesn't have appreciable velocity gradients, we can use an inviscid theory. And this is the approach that a lot of, for example, simulations have begun to take as a way of more efficiently partitioning up a problem. Okay. So to break up the derivation here, let's do a quick example involving the Euler equations. So if we're given flow in which u is equal to 2x meters per second, and v is equal to negative 2y meters per second. We assume that the flow is steady and inviscid, and that g is equal to negative, well, the vector g is equal to negative gravitational acceleration times j, that is, it's pointing in the negative y direction. Are we able to find dp dx, dp dy, and, if possible, pressure as a function of x and y? Okay. So pressure gradients and pressure itself, a unique solution to the pressure. So our solution approach here is essentially going to be first, right, well, state our assumptions, right? We're going to assume that flow is steady, rho is a constant, okay, incompressible, homogeneous flow. And our procedure, sort of in steps here, is going to be plug u and v into our governing equations, whatever those may be. Solve for dp, dy, dp, dx, and then integrate on x and y to find p as a function of x and y. So one of the things I always do in situations like this is I know, right, that when I plug u and v into the governing equations, in this case governing equation is going to be the Euler equations, what I'm really plugging in is going to be product of u and du dx and v and du dy, etc. So I like to write out a little table ahead of time that contains all of the velocity gradients sort of compiled in one location. So right, I've got u is equal to 2x, v is equal to negative 2y, say du, du dx then is 2 1 per second. dv dx is equal to 0. du dy is equal to 0. dv dy is equal to negative 2 1 per second. Okay. So at this point, I just have kind of a lookup table where once I write down my governing equations, namely rho gx minus dp dx is equal to density times du dt plus u du dx plus v du dy, and rho gy minus dp dy is equal to rho dv dt plus u dv dx plus v dv dy. Okay, notice I've left all the z derivatives and the w's out because we're assuming this is a two-dimensional flow. So at this point, it's a pretty trivial process simply to, look over at each of these terms, pull them off of our table that we wrote out, and plug them all in. So we know that, right, we've said it's steady, so in both of these cases, this goes to 0. I'm going to spread these out a little bit so I can substitute values in. we've said that gravity acts in the y direction only, right? So gravity has no component in the x direction. And also looking up here, right, we know that the du dy term and the dv dx term are both 0, so we can go ahead and cancel those out. Du dy, dv dx. So what we're left with is going to be, right, negative dp dx to rho u, which is our 2x, right, du dx, which is 2. Here, negative p dy plus or minus rho g is equal to rho times v, which is our negative 2y, times dv dy, which is equal to negative 2. And so we could solve for dp dx and dp dy, using these two equations. So carrying this over, we end up with, right, dp dx equal to negative rho times 4x meters per second squared. That's not correct. Oh yeah, the 4x meters per second squared. And dp dy is going to be equal to negative rho times negative g minus 4y. All right, so that answers the first two parts of our problem. Last thing we might want to do is figure out how to use these two gradients of pressure to get a unique expression for the pressure. So my trick for this, this is something we have to do a lot in fluids, is take two different derivatives of the same expression and use them to assemble that expression itself. My trick here is to say we know that p is a function of x and y, and so this could formally be broken up into some function of x, we'll call this f1, plus some function of y, we'll call this f2, plus some function of x and y, right? If we were to split up all the terms, it has to fit under one of these boxes. Okay. If we integrate dp dx, right, on x, we're going to end up with what? Oops. 2 rho x squared meters squared per second squared, right? Plus some function, unknown function of y. I guess plus a constant. And then integrating dp dy on y, we're going to end up with negative rho g y minus 2 rho y squared plus f1 is a function of x plus c. All right, so then to make sure that we're capturing all of the functions that go into p, I would say I would write out a little table here that's got, right, f1 of x, f2 y, f3 x, combined x and y, and then, right, we've got our dp dx dx and our integral dp dy on dy, and just fill in the boxes of the table. Take your solution to the integral of dp dx and put it in the appropriate boxes of the table. So we've got, right, -2 rho x squared. So that's a function of x only. We'd say -2 rho x squared. Okay. We didn't get any component that has a function of x and y. So we'd put a 0 here, because if there was an x in there, it would have had to come out of that integral. And we have an unknown function of y, right? Because the integral on x isn't going to reveal that. Moving down, right, the integral on y, we have as a function of y, we have rho g y minus 2 rho y squared. We don't know what our function of x is. And again, there's nothing here with an x and a y both present. So then finally, to assemble the final answer, to say, you know, we use these two pieces of the puzzle to assemble an idea of P. Simply go through each column and say, do we have an entry in this column? Yes, we have our -2 rho x squared. Do we have an entry in this column? Yes, we have our -rho gy minus 2 rho y squared. Do we have an entry in this column? Yes, we have 2. And they're both 0. And that's our litmus test to know whether we've done this right, is if you have to have an entry in every single column to know that you've fully captured all of the functional behavior of that unknown. And anytime you have more than one entry in a column, they have to match, okay? Because otherwise your integrals are inconsistent and there's been a math problem. So it's simply sum down, and we would say, right, the pressure of x and y is equal to -2 rho x squared minus 2 rho y squared minus rho g y. And then, right, there's always possibly that constant at the end.
Can you explain again the conditions that you're initially checking for that grid that you set up? You want to have every single box filled? Or?
So no, you don't need to have every box filled, because if you're integrating a function that only has y's in it, right, and you're integrating on y, you're not going to get any x's out magically. So you don't. That doesn't give you any clues about what goes the functional dependence on x. Simply saying that anything that's a function of x and y can be split into a sum of functions of x, functions of y, and functions that have both x and y. Okay? And so in order to fully define that function of x, y, in this case the pressure, you have to have some clues filled in for every possible term that can be in there. Okay. And if you have two things that point to the same term, they have to agree with each other. That's your internal check. Okay. So that does it for Euler. The next thing is the Navier-Stokes equations. All right. So I'm going to return over here, and let's go ahead and delete these scribbles that I made earlier, if I can. Nope. Erase them again. Okay. So return back to our general equations of motion. All right. So forget the inviscid assumption, where in fact we're going to be making some big assumptions about the viscosity in the steps to follow. So here we are. Equations or conservation of momentum. Sparta, laundry, and storage. I have no idea. Anyway, so we've got our conservation of linear momentum. Again, F equals ma. And in order to deal with these 12 unknowns that we have here, instead of eliminating them, we're going to try to inject some other model that helps relate our shear stresses to the velocities somehow. Okay. So doing this is going to rely on these fluid kinematics that we discussed a little while ago. Namely, this guy right here, okay, the angular deformation. So previously, right, we said that the angular deformation, gamma dot, is a tensor. It can be written as dvi dxj plus gbj dxi. Okay, and this indicates the rate at which the shearing strain of a fluid element occurs. Now, if we remember back in chapter 1, in the first 1 or 2 days of class, we defined a Newtonian fluid. Okay, in a Newtonian fluid, the definition was that the shear stress is proportional to what? The rate of strain. Okay, this is what differentiates a fluid from a solid. Solid stress is proportional to the strain. Fluid is proportional to the rate of strain. So we've defined what the rate of strain is. And this, allows us then to link tau ij, okay, under this assumption of a Newtonian fluid can be linked to gamma dot ij. Now, the specifics of this relationship, I would like to say they're as simple as tau ij is equal to the viscosity times gamma dot ij, but there's one little complication. So I'm going to go ahead and throw this up here. The typical assumptions, and this is where this is why I can't quite say that. So the shear stresses, right, over here on the upper right, they do follow this relationship, where we say simply that tau ij is equal to mu times gamma ij for I not equal to j. That is, for shear stresses, it's simply the viscosity times the rate of strain. Just like we did before, right? We said that the shear stress was equal to gamma times, in most cases, du dy. Right? That was for a 2D flow. The normal stresses, they have that component, that viscous component here, but they also have that pressure, okay? Because there are really two things that are pushing and pulling on a fluid element. One comes from that viscosity, okay? And the other comes from the inviscid pressure influence. And so, but now, right, we've got expressions for sigma xx, sigma yy, sigma zz, and we've got expressions for all of the taus that go into our stress tensor. In other words, we have something to plug into. Into every single one of the terms on the left-hand side, okay, that comes back to the velocity of the fluid. So, if we plug in those expressions that we just saw on the previous slide, those are in the book as well. If we plug in those expressions, then we get now, right, for example, the x component. We'll concentrate only on the x component now, and we'll generalize it to the y and z. Right, our original equation of motion was rho gx minus d dx of sigma xx plus, sorry, that was a plus. X dy plus d dz rho du dt plus mu du dx plus v du dy plus w du dz. Okay. We're replacing these terms right here with those expressions from a Newtonian fluid. So what we're going to end up with now is rho gx minus d dx of p minus p plus 2 d dy of mu du dy plus dv dx plus d dz mu du dz plus dw dx, okay, is equal to the same right-hand side that we have written above. Okay, so there's our Newtonian fluid model. Now, if we wanted to expand all of this out, it gets a little bit messier, and so that's the reason I'm only going to do this for the x component. We would say we've got rho gx minus dp dx plus 2 mu squared u dx squared plus mu squared u dy squared plus mu d squared v dx dy plus mu d squared u dz squared plus mu d squared w dx dz. And is that going to be all of it? Yes, it is. So I'm going to take all of the terms here. So I've got all the terms that have a ddx present in them. Okay, I'm going to underline. And all of those are a second derivative. I'm going to underline. Okay, in blue. So we've got a mix here of derivatives of x and cross derivatives of x, y, and x, z. Okay, so I'm going to split those into two groups. Rho gx, so this is equal to, right, the same right-hand side. If I split those into two groups, dp dx plus viscosity d squared u dx squared plus d squared u dy squared plus d squared u dz squared. Okay, those are all the blue underlined terms. Notice that this guy's been underlined twice because it can be considered a, right, it's a dx, it's a derivative of x, okay, but it's also a second derivative. And that factor of 2 out front means I've got two of them to work with. So I put one of them in here, and I'm going to group the other one into the next set of terms, which is written dx du dx plus dv dy plus dw dz. Right, equal to the right-hand side. Okay, there's one more assumption we make in order to get to the Navier-Stokes equations. We're just seconds away from it, and that's the assumption of an incompressible flow. Okay, Navier-Stokes, as we're deriving it, applies to incompressible fluids. And for an incompressible fluid, what happens to this term right here? Or I should say, how can we write this term? Could we say it is ddx of grad dot v? And grad dot v for an incompressible flow is 0, right? It's the idea of the continuity equation for incompressible flow. We grabbed that before. So this goes to 0 for incompressible flow. And we end up with the Navier-Stokes equation. So the x component written rho gx minus dp dx plus mu d squared u dx squared plus d squared u dy squared plus d squared u dz squared is equal to, and now the right hand side we would say is rho, right, du dt plus u du dx plus v du dy plus w du dz. Okay, so for the x direction, again, this is simply f equals ma. This is the same acceleration term we've been working with. Hopefully we're comfortable with that. And now we just simply we've got our body force, right? The force due to gravity, and we've got our surface forces due to pressure, and now the shear stresses. Instead of writing them out as tau ij, tau ji, etc., we've plugged in this expression for Newtonian fluids. It allows us to tie those shear stresses back to the velocities in the fluid. Okay, so this saves us a ton of unknowns. We basically said we've got more equations to work with. Those for Newtonian fluid, and we've substituted those in. Okay. The y component, rho gy minus dp dy plus, this is the only time I'm going to write these out full form by hand. V dx plus d squared dy plus d squared z v v rho. Z component, rho gz minus p gz plus mu W. Okay. So here we have it. This is the set known as the Navier-Stokes equations. They're famous throughout all of fluid mechanics because if we assume the flow to be incompressible and if we assume it to be Newtonian, okay, which are pretty good assumptions for things like water and even airflow at low speeds, okay, then this is, to the best of the abilities of modern science, the exact equations of motion for a fluid. Okay. Now, why are these more useful than the general equations of motion we had before? Well, if we count up the number of unknowns, basically now we've got P, all right, U, V, W. We've got only 4 unknowns. We still only got 3 equations to work with. But we can bring in one more equation, and that is, right, conservation of mass, or the continuity equation, which says, right, that du dx plus dv dy plus dw dz is equal to 0. There's our 4th equation. So now we have 4 unknowns, 4 equations. This is now a well-posed problem. This is something where if we possess the mathematical chops, we would be able to fully solve for the pressure and all 3 components of velocity in a fluid. Now, the other way we can write this is, again, so let me go ahead and box this off and say what we're working with here. Okay, so this is the Navier-Stokes equations. The Navier-Stokes equations can also be written in vector form. Sorry, my hand is tired. My handwriting's going to crap here. In vector form as rho g minus grad p plus mu grad squared of v is equal to d or rho dv dt. Okay. So this now is capturing all three of the Navier-Stokes equations that we wrote above for the x, y, and z components. But of course, the fact that it's in vector form makes it a lot harder to actually understand. Right? It just sort of hides the complexity of the equations. It makes it look quite simple, actually. Okay, so this is a good point at which we're going to stop. But I wanted to say, so we've set up the Navier-Stokes equations. Okay, this is the preview for next week, motivation. We set up the Navier-Stokes equations. That was the point of this week, was to get here. I have to tell you now, as I've hinted at before, the thing with these equations is they're coupled, nonlinear partial differential equations, and modern mathematics don't have a way to solve that sort of equation. Okay, there's no general universal solution to the Navier-Stokes equations at all. So what we're going to do next week is pick out a few special problems. They're very classical problems where the problem setup just happens to be such that we can make enough major simplifications that we're actually able to solve the Navier-Stokes equations. But in all of fluids, there are maybe 70 or 80 of these problems for which we actually have a solution. We're going to talk about a few of them next week. In the meantime, have a good weekend.